let's jump right in. If you were to strip away the sleek exterior of a modern vehicle, you wouldn't just find an engine and some gears, right? You'd find a highly complex, rolling computer network. We're talking dozens, sometimes over 100, independent electronic control units, or ECUs, constantly tweaking everything from your anti-lock brakes to the AC. But here is the ultimate engineering nightmare. How do you get all these separate computers talking to each other without turning the car's guts into a massive, heavy, totally unmanageable web of copper wire? Well, welcome to this explainer. Today, we're demystifying the Controller Area Network, or CAN bus. By the end of this, you'll know exactly how this protocol solves the wiring nightmare, how it handles errors on the fly, and the one major limitation you've absolutely got to avoid when designing your own high-data systems. To really get why CAN is such a game changer, we have to look at the massive headache it was actually built to solve. Up until the 1980s, cars really had very few electronic units. But as tech evolved, engineers used point-to-point wiring. Think about that for a second. If ECU A needed to send a signal to ECU B, you literally ran a physical copper wire between them. Need to send 3 different signals? Yep, you're running 3 separate wires. Scale that up to dozens of computers, and suddenly your wiring harnesses are impossibly thick, insanely heavy, and just an absolute nightmare to manufacture or troubleshoot. It was, quite frankly, a completely unscalable architecture. So, the fix arrived in the 1980s when Bosch stepped up and developed the Controller Area Network, or CAN. Instead of running a dedicated wire for every single connection, CAN introduced a robust, inexpensive serial bus system. Imagine it as creating one single unified data highway. Every ECU taps right into this exact same highway. It completely flipped automotive engineering on its head, stripping out literally miles of heavy copper and replacing it with one standardized digital network. Section 1. Core Concept: the Broadcast Network. So you might be wondering, how exactly does a shared highway not immediately devolve into absolute chaos with 50 computers trying to yell at the exact same time? Well, by definition, CAN is a field bus system realizing serial communication. But what actually makes it special is that it's engineered to work flawlessly over larger distances and, crucially, under highly unfavorable electrical conditions. We're talking about the crazy, electromagnetically noisy environment of a running car engine. And, unlike older centralized networks where a single master computer bosses everyone around and dictates who speaks, CAN is entirely decentralized. Every single node on the cluster is an absolute equal. And that brings us to our never-forget visual analogy for this explainer: the town hall meeting. Imagine a crowded town hall. When someone has an announcement, they step up to a microphone and just broadcast their message over the loudspeakers to the entire room. They don't walk around whispering in individual ears, right? Every single person in that room hears the announcement. This is exactly how CAN works. It uses broadcast transmission. When a node sends a frame of data, every other node on the bus receives it. But here's the genius part. Just like in a town hall, if the announcement is, "Hey, a blue sedan is blocking the driveway," only the owner of that specific car stands up and does something. Everyone else hears it, ignores it, and gets back to work. In CAN, every node checks the identifier on the broadcasted frame and only processes the data if it's actually relevant to their specific programming. Section 2. Rules of the Protocol: how CAN maintains order. Okay, so keeping that town hall analogy in mind, what are the hard rules that keep communication flowing smoothly without everyone talking over each other? First off, it's event-driven. Nodes don't just sit around twiddling their thumbs waiting for a scheduled time slot to speak. They only transmit when a specific event happens, like boom, you just pressed the brake pedal. Now, we already touched on broadcast transmission, but these next 2 points are where CAN really shines for real-world engineering: built-in error detection and immediate error signaling. Since safety is absolutely critical in vehicles, CAN doesn't wait around for some higher-level software to figure out if the data got corrupted. The error checking is baked right into the hardware protocol layer itself. So let's walk through how this error handling actually plays out mathematically and mechanically, step by step. Step 1, the absolute millisecond a frame is received, the receiving node checks it for errors using built-in math, like cyclical redundancy checks. Step 2, if an error is detected, it is flagged immediately on the bus. Step 3, this instantly triggers the defective transmission to abort right then and there, and a retransmission kicks off. But step 4, this is the real magic, the self-healing cluster. See, every single node maintains internal error counters. If a specific node starts throwing way too many errors, maybe its wiring got chewed up or a chip is dying, that counter ticks up. Once it hits a specific threshold, the protocol literally revokes that node's right to send. It physically mutes it from the bus. That ensures one broken node can't just spam the network and take down the entire town hall meeting. Section 3. Evolution and Application Walkthrough. A system this bulletproof wasn't going to stay locked inside passenger cars for long. The history of CAN is honestly a masterclass in industry adoption. The very first protocol development started back in 1981, initially aimed at manufacturing automation. But by 1983, Bosch saw the massive potential for automotive networks and totally pivoted. The big, real-world proof of concept dropped a decade later in 1991, when CAN saw its first serial production run in the Mercedes-Benz S-Class. It was a massive hit, proving a single digital bus could handle the intense demands of a high-end luxury vehicle. By 1993, it was globally locked in under the ISO 1189 standard, securing its spot as the ultimate blueprint for automotive communication. And because it was standardized, incredibly reliable, and incredibly cheap, the idea spread like wildfire across other industries. If you look at the different applications out there today, it's wild. Designing systems for massive agricultural harvesters or tractors? You're going to use Isobus, which is entirely based on CAN. Wiring up marine electronics for ships? You'll use NMEA 2000. Yep, built on CAN. Railway door controls and passenger displays rely on IEC 6137533, using CAN Open. Even industrial factory floors use DeviceNet and CAN Open to run conveyor belts and robotic arms. It has truly become the universal language of robust, event-driven machinery. Section 4. The CAN Payload Gotcha. All right, pay attention, because here is the exact trap that catches so many young engineers when designing high data systems. The number 8. A standard CAN frame has a maximum payload of exactly 8 bytes of data. That's bytes, folks, not megabytes, not kilobytes. 8. Individual bytes. This constantly trips up engineers who are used to massive, modern Ethernet data pipes. Listen, you cannot use standard CAN to stream a high-definition backup camera feed or efficiently push massive over-the-air software updates. It's just not built for that. It is designed purely for short, highly reliable, lightning-fast control signals. Think a 4-byte message that says, steering wheel turned 15 degrees, or deploy airbags right now. If you try to shove massive amounts of data through CAN, you will completely choke your network. Always, always remember that 8-byte limit when scoping out your projects. Section 5. Summary and final takeaways. We've covered a ton of ground today, from heavy copper wire nightmares to sleek, decentralized networks. Let's rapid-fire recap the 3 absolutely critical takeaways you need to lock in. Number 1, CAN is a broadcast network. Always remember the town hall meeting. Every node hears the message, but only acts if the identifier is actually relevant to them. Number 2, it is inherently self-healing. The hardware-level protocol instantly catches errors, and those built-in error counters will automatically isolate and mute a defective node before it can drag your whole cluster down. And number 3, it's a universal standard. Mastering CAN doesn't just mean you can build cars, it means you've got the skills to engineer control systems for ships, trains, and industrial robotics anywhere in the world. Understanding these foundations is exactly what separates a good engineer from a truly great one. If you found this explainer helpful, make sure to hit subscribe to our YouTube channel, Spectrum Speak, for more EMC and automotive communication protocol survival guides. But I'll leave you with this final thought. As modern cars rapidly transition into massive rolling data centers packed with sensors for autonomous driving, will the 8-byte workhorse of the CAN bus survive, or are we on the verge of a completely new networking revolution? Keep building, keep questioning, and we'll catch you in the next explainer.